So we're going to pick it up where we left off. Obviously, I don't just want to pick up immediately from where we left off. We'll just kind of ease ourselves back into it a little bit. But I'll spend today doing a couple more examples of how we're solving differential equations using the Laplace transform method. Okay? So, just remember what happened. So a very quick look again at some of the stuff. We introduced this transform called the Laplace transform, which is defined in definition 2.1 up there. It takes a function depending on a variable t, the f of t here in this definition, and it produces a function of a new variable s out of it. Okay, using this integral here, the integral from 0 to infinity of e to the minus st, e to the minus st times f of t dt. So this is the first thing. The definition of the Laplace transform is this integral. And when we do the third part of the unit, the Fourier transforms and Fourier series and Fourier transforms, we'll meet other transform objects like this. We'll be able to talk a bit more about them. You'll recall that, straight away, I mean, there's a question to answer given any particular function, whether this transform is a valid object or not, whether this integral converges, because you're integrating over an infinite range. So this integral might possibly diverge. So it's a bit of an issue to settle when and where these integrals converge. But for most of the functions that we meet, these integrals do exist, or they exist at least for certain values of s. Okay. If you go forward a couple of pages, when we did some work with finding Fourier transforms of particular functions, we took the constant function, we took the function f of t equals t, f of t equals t squared, and so on. We took the function f of t equals an exponential of t. So we worked some various examples straight from that definition. Then we also proved some results about the transform. And between finding transforms of some basic functions and putting these together with the results, you can build up this table of standard transforms. So there's a two-page table here, a couple of pages into the chapter. So down the left here, you have some standard kind of family of functions down the left, and their Laplace transforms, these functions of s, down the right-hand side. Then on the second, there's some things we haven't met there yet, this thing called the step function and the Dirac delta function. We'll meet those soon enough. And on the second page there's a summary of some of the important properties of the transform. Okay, so this is like a toolkit that's available to you to use, these properties of the transform and transforms of standard functions on the first page of the table. This is like a toolkit, a bag of tools that you can use when you're solving differential equations using this method. Okay, so when we're going through the examples, we'll be coming back and referring to this lots of times, and it's something you should become practiced in. And this is the table that you'll have in the formula handbook in an exam situation if you're answering a question based on these ideas as well. So there are many properties that the Laplace transform has, but just to lead us into doing these examples of solving differential equations, I just want to emphasize two of them. So two key properties. The first one is that the transform is linear. I.e., if you transform a linear combination of two functions, if you have two functions f and g, which you know how to transform, and you form a new function that's some kind of linear combination of the two of them, the transform of that is just the linear combination of the individual transforms of the functions f and g. So this is for functions f and g that have transforms. And for a pair of scalars, alpha and beta, from the real numbers. That's the first key property, and that's that comes into play right at the start of the method, which we'll see shortly. The other key property which we proved was the transform of derivatives property. This was, what was it? It was one of these theorems. Theorem 2.3. We'll just remind ourselves there. Well, this said if the Laplace transform of a function little f of t, supposing that's equal to capital F of s, then this property told us what the transform of the derivative of t. And it's something very closely related to the transform of f. Very closely related to this function, capital F of s. It's simply s times capital F of s minus the initial value f of 0 of the original function f. Okay, I won't go through the proof again. We discussed it last term, and the proof is in the notes. And this also extends to higher derivatives as well. So the second derivative, the transform of the second derivative, d2f dt squared, this is s squared times f of s minus s times f of 0 minus f prime of 0, where f prime is the first derivative of the function f. And these properties, these are summarized there. It's on the projected screen there. Again, slightly different terminology. There's quite a mixture of terminologies and notations that are used, so it's good to be familiar with them all. So this is equivalent to different notation, equivalent to the different notation on the table, where we see that the Laplace transform of a derivative dx dt, so here in the table it's written as s times little x bar minus, it's got written x with a subscript of 0. But this result here is exactly the same as this result up here. It's just slightly different notation that's used. Okay, here we're using capital F to denote the Laplace transform. Here in the second one, as it says in the top of the table there, up here, that the original function letter with a line over it stands for the Laplace transform of that function as well. Okay, so that's where x bar is the Laplace transform of x. And the x with the subscript 0 stands for the initial value of x. That's that notation is repeated at the bottom of the table there. So it's potentially confusing having these different notations floating around, but different authors and different books use different notations. So it's good to be exposed to some of the commonly used ones. Because the main thing is don't get too particularly wedded to any form of notation. Try and remember the result, in a kind of notation-free manner. It's saying that the Laplace transform of a derivative of a function is the new variable s times the transform of the original function, before you took its derivative, minus the initial value of that function. So this is the second key property we want to remind ourselves this afternoon of. And this is very relevant for solving differential equations, of course, because differential equations are combinations of derivatives of different orders of an unknown function, and you're trying to find that unknown function. Okay. So is that okay? Any questions about that at this stage? Okay. Okay, so we went on. So if you go forward to page 48 then. Page 48 lays out in kind of 4 steps what the procedure is for solving one of these differential equations. Okay, so this is what we're going to follow now. We're going to do an example of solving a single ODE, and then we should have time to do one solving a system of a pair of ODEs, a pair of what's called coupled ordinary differential equations. So what are the 4 steps? Well, so we're trying to solve something like this ODE here in 2.24. Typically, they'll only be of order 2 or order 1, involving first or second derivatives of the function. But potentially, we can handle ODEs of any order. They have to have linear coefficients and maybe, sorry, not linear, constant coefficients. So these A's multiplying the derivatives here are fixed real numbers, fixed constants. Although potentially the term which doesn't depend on y at all, that can be a non-constant function of the independent variable t. So the first step is going to be to take the transform of the whole equation. Okay. So say the transform of the left-hand side of that equation is equal to the transform of the right-hand side. Okay. Then we bring in any initial conditions that we're provided with. And then what we'll have, because we've transformed the equation, we now have an equation which doesn't feature derivatives of y anymore. Now it's an equation featuring the object y bar, which is the Laplace transform of y. But it's been converted from what was a differential equation into now just some kind of, an algebraic type equation in y bar, because there aren't different derivatives of y bar appearing in the transformed equation. So the derivatives all kind of disappear from view temporarily. So we can just proceed using ordinary algebraic manipulation to solve the transformed equation for y bar. And then in principle, there's just one remaining step, is to take the inverse transform then, because we'll have found y bar as a function of s, to take the inverse transform of that to recover the original unknown function y as a function of the independent variable t. Okay. Now in example 2.6 there's a fully worked out example, which we talked through in the lectures. But I'd like to do another example now, which is example 2.7. Just to talk you all through that. So this will be going through that 4-step procedure. And looking out for the occurrence of those 2 key properties of the transform as well. Okay. So we start with this equation, dy dt plus 2y equals 4. So y is the unknown variable, the unknown function. T is the independent variable. So we're looking to solve for y. And it's subject to the initial condition y of 0 is 3. So the first step is to transform the whole equation. So very roughly, you say the Laplace transform of the left-hand side is the Laplace transform of the right-hand side. Okay, just hit both sides with the Laplace transform. And now the first of those key properties comes in, is that the transform is linear. So on the left-hand side, because these ODEs are ones with constant coefficients, what we just see here is a linear combination of different derivatives of y. So we can split that up into the Laplace transform of dy dt plus 2 times the Laplace transform of y, and that's equal to the Laplace transform of 4. So that's by the linearity of the Laplace transform. So at this stage now, we've got an equation which is Laplace transforms of individual basic kind of objects. So we can start filling in what those transforms are, taking results from the table as necessary. Okay. So if you look on the right-hand side of that equation, going back to the table. So on the right-hand side of that equation, you've got the constant 4. Well, the Laplace transform of the constant 1 is 1 over s. And so since it's linear, the transform there is just 4 over s. What's the Laplace transform of y? Well, we don't know what the Laplace transform of y is because we don't know what y is. The object of this whole game is to try and find the unknown function y. So we don't have any information on y at the moment. So we'll just write, and it's just a bit simpler notation, y with an overbar. That's just standing for the Laplace transform of y. So y bar stands for the Laplace transform of y. It's just quicker and easier to write that down rather than curly L bracket y bracket, just y with a simple overbar. But having made that decision, then we're able to put down a related expression for the Laplace transform of the derivative of y, okay, using that second key property that we just outlined on the previous page, which was the transform of derivatives property. So the Laplace transform of dy dt is s times y bar minus y of 0, the initial value of the function y. So we've achieved that first step there, which is taking the transform of the whole equation. And we now don't see a differential equation, which we're trying to solve. We now just see an algebraic equation. So there's just one unknown object there, which is the function y bar. S is this new variable. Y naught is a constant which has been supplied to us, and then there's a few other constants. Okay. So we should bring in this initial condition now and start to simplify the equation. So we got y bar, and that's got a coefficient of s plus 2, multiplying it. And we've got minus 3 equals 4 over s. Substituting in the initial conditions. That initial condition, y of 0 equals 3 up at the top. So now we just want to solve this algebraic equation for the unknown y bar. Okay, so there's y bar over there. I just want to shove everything over to the other side and get a nice enough expression in s for the function y bar. So that would be something like y bar is, have to bring plus 3 over the other side, so it's going to be 4 plus 3s up there. You've got an s in the bottom, and then you're dividing both sides by s plus 2. So just algebraic manipulation to solve that equation. Okay. That's good, we've solved it. There it is. So in principle now there's just one remaining step. That remaining step is just to take the inverse transform of this function y bar. So we'll turn to that now. But any questions about how we arrived there, or anything you'd like clarified about any of those steps? Yes. Yeah, so that's, well, because I've got s times y bar here, and I've got 2y bar there, so I'm just bringing them together. Yeah, so there's a, so in total I've got s plus 2 times y bar. Yeah. Minus 3, stick the 3 over. Okay. So this is good. This is like an intermediate solution. We've solved the transformed problem. So normally then we think of taking the inverse transform as where we come back to the table of transforms. So can we find this function 4 plus 3s over s times s plus 2? Can we find that anywhere down the right-hand side? Well, not exactly. Nothing down the right-hand side there. Nothing down the right-hand side there matches this form here. That's because, well, we need to do a bit of simplification on this first. So in order to, before looking for y bar on the tables, we first find its partial fraction expansion. Okay, because this kind of function here is a rational function in the variable s, and we want to get that as, to express it as a combination of the simplest kind of rational functions, and all the simplest kinds of rational functions in S are all contained there on the table. Okay, so once we know the partial fraction expansion of this, we'll be able to find each of those component parts of it on the table. So it's going to be something over S and something over S plus 2. And these will just be constants, constants in each case, because the degree of the numerator is degree 1 in S, and the degree of the denominator is 2 because it's quadratic. So the numerator is has degree less than or equal to the denominator. So the numerators in these simple partial fraction bits will just be constants. So you can think of that as an alpha over S plus a beta over S plus 2. So now we'd need to go through a bit of an algebraic process now to find alpha and beta. Now, this one happens to be not too difficult. When you write it again as a single fraction over this common denominator, you've got alpha times S plus alpha times S plus 2 alpha plus BS. So what's that? That's alpha plus beta into S plus 2 times alpha. So this numerator here is supposed to equal 4 plus 3s. So can we arrange that in any way? Yeah, you don't need to go to Gaussian elimination or anything. We can see that this implies that alpha should be 2 and beta should be 1. Okay, so there's some fairly nice solutions which are easy enough to find, but in principle or in general, you might need Gaussian elimination here. Especially if there are many individual fractions in the partial fraction expansion, so many unknown constants there to find. Okay, so now we have a very good description of this function y bar. So y bar now is 2 over s plus 1 over s plus 2. So now we can just go and find these on the table of Laplace transforms, okay? So we can say we can take the inverse transforms now. Take the inverse transform of y bar to recover y. Okay, the solution to the original ODE is the inverse transform of y bar. Because the transform is linear, well, then the inverse transform is linear as well. So this is 2 times the inverse transform of 1 over s plus the inverse transform of 1 over s plus 2. And these are found on the table, okay? 1 over s is the Laplace transform of the constant 1. So this 2 here is just the constant 2. And 1 over s plus 2 is the transform of e to the minus 2t. Okay, so that's our final solution to the original differential equation. If you check, you can confirm that it is. We can be confident we haven't made any errors there, because we can always validate it by substitution into the ODE, taking that value of y, putting it into the original ODE, see that you get the same thing on both sides. So you can validate it by substitution into the original ODE and checking the initial condition that was given. The initial condition, remember, was that y of 0 had to be 3. That's 2 plus e to the 0, which indeed is 3. 2 plus 1. So that checks as well. So we can be confident enough that we didn't make any errors there. So from start to finish, that's the method for solving these equations using the Laplace transform. Now, other examples might be more complicated because the original ODE that you're trying to solve might have a higher order. So it might have a second derivative or a third derivative involving y in it as well. So that will mean that the transformed equations will have s squareds or s cubes in them. So it's a more complicated algebraic equation to solve, but in principle, the method just goes through in the same way. Okay. I guess the higher order the ODE is, potentially the more complex rational function you're going to get here. And so potentially the partial fraction expansion is going to be potentially much bigger. So it's kind of more complicated, but in principle, just the same concepts. So any queries I could answer on that, or any clarification I could give? Okay. So let's do another example. So see on page 50 then, there's a second example, but this time we're not solving a single ODE, but rather a system of ODEs. This is example 2.9. Now, in principle, here we just go and do the same thing. Okay. So this system. Now you'll notice here that both equations refer to both of the unknown variables x and y. So that's why the equations like this are called coupled equations. So you've got the two unknown variables x and y, and you've got two ODEs describing them. But they both appear in each of the ODEs. So we have to consider the pair of differential equations together as a system. Maybe I'll just label this as A and B. Subject to the initial conditions that are y of 0 is 2 and x of 0 is minus 3. Well, the procedure is just the same. You take the Laplace transform of both equations, stick in the initial conditions as they arise, simplify the equations, and then what we'll have is a pair of algebraic equations in the two unknowns, x bar and y bar, which in principle we should just be able to solve using algebraic manipulation to identify what x bar is and what y bar is as functions of s. And then, with the help of our table and partial fraction expansions if necessary, find the inverse transforms of x and y to recover the two functions x and y that solve this system. Okay. So the first step is to transform both equations. We'll write x bar for the Laplace transform of x and y bar for the Laplace transform of y. Well, equation A, the first ODE implies that s times x bar minus x of naught plus 4 times s of y bar minus y of naught plus 5x bar equals 3 over s. The transform of the first equation, the transform of the second equation. So equation B implies that s y bar minus y of 0 plus 3x bar plus y bar. Now the transform of the function t is 1 over s squared, is it not? Brain. 1 over s squared, yep. So the transform of 2t is 2 over s squared. So that looks a bit messy there. There's simplifications we can do. So we can bring in the initial conditions, which were given. Y of 0 is 2, x of 0 is minus 3. Bring those in and collect together like terms. So if there's x bar appearing in a few places, collect it all together and look at the combined coefficient of x bar, and the same for y bar. So in the first equation, we see s plus 5 times x bar plus 4s y bar. And in total, on the left-hand side, there's a constant of 3 minus 4 times 2. So 3 minus 8. So there's a minus 5 on the left-hand side. So if I take that across to the other side, that minus 5 will become a plus 5. So I can write it as 3 plus 5 times s and put that all over s. Just tidies up equation A a bit so that there's only x bars and y bars on the left-hand side. And then the second equation, doing a similar thing there. So multiplying x bar, there's just a 3. And multiplying y bar, there's an s plus 1. And there's a minus y bar, which is there's a minus 2 on the left-hand side. So if I put that over the other side, it becomes a plus 2. It's 2 plus s squared all over s squared. Okay. that okay? Are my S's and 5s distinguishable? That one there, that's an S. So that's multiplying the Y bar. That's the S that comes from the transforms of derivatives property. Okay, so you tidy it up, you bring in the initial conditions, but now we want to solve this. So solve these for X bar and Y bar. So we just need to eliminate one of the variables. So we could eliminate the X bar by considering the combination S plus 5 multiplied by equation B minus 3 times equation A. Okay. So if you just focus on the X bar bit, when you multiply B by S plus 5 and A by 3, that makes the coefficient of X be the same, of X bar be the same. So when you subtract them, then the X bars will disappear. So this equation, S plus 5 times B minus 3 times A. So this becomes drift across here just to give myself some room. So multiplying Y bar here, we're going to have 4S S plus 5 times Y bar. Then we're going to be subtracting 3 times this. So subtracting 3 times S plus 1 Y bar. The X bars cancel out. And then I just have to do the right-hand sides. So I've got 3 plus 5S multiplied by S plus 5. And then I'm subtracting. No, that was the wrong one, sorry. On the right-hand side there, I've got 2 plus 2S squared. And that's multiplied by S plus 5. That's all of it over S squared. And I'm subtracting 3 times the right-hand side of A. So I'm subtracting 9 plus 15S over S. Why did you wait till I was finished? Why didn't you scream at me at the beginning? Okay, so here it is. Okay, so that's the correct equation. So there's a bit of algebraic simplification we have to do here. But in principle, we're quite close to the solution for Y bar here. So what do we have multiplying Y bar on the left-hand side? Well, you've got an S squared, you've got a 6S, you've got a 5 minus a 12. Oh, no, sorry, you have a 6S minus 12S. You've got a minus 6S. And then you've got plus 5. Multiplying all that out. Should we start Say what? Sorry, what? Well, I haven't made an error yet, have I? No, that's good. Should I combine these together now? Yeah, maybe I should. So I've got s squared there. I've got 2 plus 2s squared. Maybe I won't multiply out those yet. And I got a minus 9s minus 15s squared. Okay, we're kind of ready there to approach our final solution for y bar. I've got an s squared there, and I'm dividing by this, but I may as well factorize it at the same time. It's s minus 5 times s minus 1, isn't it? Isn't that right? Yep. So I'm dividing both sides by that, and it factorizes as s minus 1 times s minus 5. And then tidy up the upstairs. The upstairs is going to be a cubic. I'm going to have a 2s cubed s squared. I'm going to have a 10s squared minus 15. I'm going to have minus 5s squared. A few s's. I'm going to have a 2s and a minus 9s, which gives us a minus 7s, doesn't it? Then any constant there is a constant 10. That look halfway plausible? Because it's 2s squared times 5 is 10s squared minus 15s squared is... Yeah. Okay, so there's our function y bar. Woohoo. So in principle now, ready to take an inverse transform to find y of t, except, well, of course I lie, we're not ready. This function is too complicated to, it's not listed as it is on the table of Laplace transforms. So rather, first have to find the partial fraction expansion. Partial fraction expansion of y bar. So that will allow us to find y bar as something, an a over s plus a b over s squared plus a c over s minus 1 plus a d over s minus 5. So we'll have to go ahead and find those coefficients. But having found them, then each of these individual functions here are listed on the table. It's a constant term, a t term, and 2 exponential terms. And then we must also return to recover x of t as well. So it can be quite a drawn-out process, this. So I'll leave you to finish it. And we'll look at it next week, okay? But you're just a few steps away from hitting out the final solution there. But we'll see that through to the end when I see you next time.